Good morning, everyone. It is my pleasure to welcome everybody on behalf of the Béla Institute at the presentation ceremony of the 2024 Béla Szőkefalvi-Nagy Medal. I would like to especially welcome Professor Masregi, the recipient of the medal, and Mrs. Szőkefalvi-Nagy, the founder of the medal. The Béla Szőkefalvi-Nagy medal was founded by Mrs. Szőkefalvi in 1999 in memory of her father, world-renowned analysis professor Béla Szőkefalvi-Nagy, who served as the editor-in-chief of our journal Akta for 35 years, starting from 1946. The medal is awarded each year by the recommendation of the Béla Institute to an outstanding mathematician who published deep and influential papers in Akta. The medal itself is wrought silver, designed by the artist András Lapis. It's a diameter 42.5 millimeters. The upper side depicts the portrait of Professor Béla Szőkefalvi-Nagy. Its backside contains the name of the awardee, surrounded by the inscription Acta Scientiarum Mathematicarum, which is the name of the journal. Yes?
Szeretnék mondani valamit, mert valahogy ez mindig elfelejtődik, hogy van egy bordűr a hátlapon, hol az akta föl van írva meg a név, és ott az 1998-as szerkesztőség neve van fölsorolva, megörökítve inkább.
Yeah, so there's an addition to the description of the medal. It not only contains this surrounding text with the name of the journal, but on the side it includes the name of the editors. Editors in 1990 were the editors in 1999. Sure. So it is my pleasure to announce that in the year 2024, the Béla Szőkefalvi-Nagy medal is awarded to Professor Masregi from Laval University, Quebec City, Canada. First, I would like to ask Professor Lajos Molnár, editor-in-chief of Akta, to describe the scientific achievements of Professor Masregi.
Thanks, and you can see the medal there and also the description of what Professor mentioned. And let me just survey the basic, the most fundamental achievements by Professor Masregi, scientific achievements and the professional activities what he was doing over the past decades. So you can see here that the recipient of this year is him, and let me emphasize that this is the 25th medal. So the announcement concerning this announcement reads as follows. Masregi is a leading researcher in several areas of function spaces. He's an operator theory. He has achieved seminal results in bibliographic Banach spaces, the functions of the unit disk, as well as the linear operators. He's well known worldwide for his numerous books, having authored one monograph and 12 textbooks written for researchers and graduate students. And according to MedSciNet, this is the current number. He has 135 papers with publications, not only papers, with around 1,200 citations. And he received several awards and distinctions. He currently holds Giovanni Prodi Chair at the University of Würzburg in Germany, Canada Research Chair at Laval University. He's a lifetime ANS Fellow, Fields Institute Fellow, and CNS Fellow. He was a Fulbright Research Chair at Vanderbilt University, recipient of the IEEE Prize Paper Award, and most notably, maybe he was the president of the Canadian Mathematical Society between 2020 and 2022. And in the past 3 years, he published 4. So in 3 years, he published 4 important papers in Akta, and one of them was a significant contribution to the 100th anniversary issue of our journal, and he was one of the speakers at the meeting celebrating that memorable event. Okay, so about his research activities, his main research interest, so he has a wide, broad research interest. The main areas are complex analysis, functional analysis, applied harmonic analysis, and matrix theory. If you see his activities, his research papers and publications are not signed, they are categorized into certain groups, and the table says that obviously the largest number of papers, these papers and publications, come from the area of functions of the complex variable. Next area is operator theory, functional analysis, but you can see such areas like, for example, difference and functional equations, operational research, and even combinatorics. There is a paper which is related to combinatorics. In the description of his Canada Research Chair position concerning the main research area, which is function spaces, one can read the following. Function spaces are an active area of mathematics. They encompass the major components of harmonic and functional analysis, operator algebras, approximation theory, several complex variables, and real algebraic geometry. They also provide the foundations of many areas of applied sciences such as system theory, signal and image processing, telecommunications, and modern control theory. So there are applications in several areas. As for his short vita, so he received his bachelor degree in electrical engineering in Tehran, and then turned to mathematics, and in 2001 received a PhD in pure mathematics at McGill University in Canada, and he from 2001 continuously is affiliated to, his positions are in Laval University, but during that period he had several visiting invited positions. You can see the list of the places, so in Europe, in North America, several places. As mentioned, he received several awards and distinctions. Here is the list of them. I already speaking about them. And as for the academic service, I also mentioned that he was the president of the Canadian Mathematical Society. As for current services, he's the editor-in-chief of Canadian Mathematical Bulletin, and also an area editor at the proceedings of AMS. He's the coordinating editor of analytics, and previously he had several positions in the grant agency in Canada. Okay, so I also mentioned that he is the author of one monograph, and you can see actually two monographs, because there is one which is already in the practical form, and here is the list of the monographs and books. You see here several books published in Oxford University Press, Springer, AMS at Cambridge University Press. And he edited, I don't know how many conference proceedings, many of them. And the publisher of the recent book, Theory of Empty Spaces, introduced him on the cover of the book as follows. Javadon Shrege is an esteemed mathematician and author renowned for his work in the areas of functional analysis, operator theory, and complex analysis. He has made significant contributions to the study of analytic function spaces and the operators that act upon them, and then list previous prestigious positions he had. Okay, and now let's turn to some of his papers and mention some of the results. Actually, it's very difficult to speak about his results because that's a rather special area of mathematics, but I tried to mention a few of them. So in this paper, which appeared in the Journal of Functional Analysis, they consider certain problems concerning Toeplitz operators. Toeplitz operators form one of the most important classes of linear operators. So if we have the unit circle and we consider the L2 space of them, then the hardest space is the subspace of L2, which consists of functions whose Fourier coefficients with negative indices are all 0, and the multiplication operator M phi on L2 that corresponds to an L infinity function, phi, when restricted to the hardest space and composed from the level projection from L2 onto the hardest space, is called a Toeplitz operator. Anyway, Ries introduced the notion of general hardest space is HP. I mean, the notion comes from, the notation comes from him, and presented some of the fundamental results in his paper, which appeared in 1923. So that time, Ries was already here in second. In that paper, they studied two important questions related to the so-called truncated Toeplitz operators. The first one was raised by Serezan and asked whether the boundedness of such an operator implies the existence of a bounded symbol, bounded phi or phi. And they showed that in the general case the answer is no, but there are cases in which the answer is actually positive. Okay, another paper that I would like to mention is this, which concerns the famous Grison-Kahn-Jeloskov theorem, which is about the automatic multiplicativity of linear functionals of Banach algebras, and it says that if we have a linear functional of Banach algebra, unit of Banach algebra, which sends the identity to 1, and which is non-zero on invertible element, then this functional is automatically multiplicative. This is a famous result. And in this paper, they gave important extension of that result for the setting of reproducing kernel Hilbert spaces. Here I would like to mention that in the past 2 days, Professor Masleri gave a short course, several lectures on reproducing kernel Hilbert spaces. We enjoyed that very, very much. And I also would like to mention that he published a related paper also in ArctaSocket in 2018. Okay, another paper that I would like to mention, the transactions of AMS, is about the zero sets of certain analytic functions. That's a very important question to try to characterize the zero sets of analytic functions. And usually, in most of the cases, we have certain sufficient conditions and certain necessary conditions. It's very rare that we have a necessary and sufficient condition. And concerning this space of analytic functions, so here we have those analytic functions on the unit disk whose Taylor coefficients satisfies this condition that the coefficients form an LP sequence. So, and you norm that space with the natural norm. This is a Banach space of analytic functions. And in this paper, they characterize the zero sets of functions belonging to that space. And in the proof, they use various tools from Banach space geometry to operator theory, although the result is about functions. And then let me quote from the review in Matzheiner about one of their books, the primer on Dirichlet spaces. It says the following: together with the hardest space and the Bergman space, the Dirichlet space is one of the 3 most studied Hilbert spaces of holomorphic functions. Until very recently, the Dirichlet space was the only one of these 3 spaces without the book covering. The volume under review successfully fills this void. The authors pick several large areas of still active research on the Dirichlet space, do a good job of collecting together similar but scattered results in the literature, and provide the reader with a coherent presentation. All topics are developed from basics, and the systematic and thorough treatment is given of each topic that is included. Now many deep results seem more practical. And this is the personal opinion of the reviewer, that after reading large parts of the book, I am able to place the didactic space in a much better context. And now papers in our journal of the Szeged. The first one is this one that I would like to mention. It's about orthonormal polynomials. They consider the so-called Dirichlet space or Dirichlet space, local Dirichlet spaces. And also in those spaces that they consider the polynomials form a dense subset. But the usual Gram-Schmidt process of orthogonalization is very difficult. And in this paper, among others, they work out a very effective different method to construct such spaces. The other one is the paper that I mentioned, which appeared in the 100th anniversary volume of our journal. And this is a survey paper, and the summary, which was written by him, is so nice. If you don't mind, let me read this, because it's such a nice explanation of dilation theory. So, analytic functions, despite exhibiting very satisfactory behavior inside their domains of definition, that is being infinitely differentiable and having power series representations, could be quite wide and show bizarre performance at the boundary points. Not being continuous at a single boundary point is the simplest of such a phenomenon. However, much more pathological behaviors are foreseeable in the frontiers. That is why boundary behavior studies have faced several obstacles since early days of complex analysis, even though in many cases the final outcome is very appealing and usually ends with profound and beautiful mathematical results. Dilation is an old technique that mathematicians have exploited to deviate from the frontiers and go deep inside the domain. Then standing within the domain and coming back from inside toward the frontiers. Since our footsteps are in a solid territory on which the functions behave well and is fully under control, one tries to better understand the boundary behavior at the frontiers. No wonder the story has many ups and downs and is filled with numerous successes and failures. Starting with the pioneering theorem of Friedrich in 1923, we provide a wide range of results which are uniformly spread over a century to tell parts of the dilation history in the complex plane. We finish with some recent results and open questions obtained in the course of the last decade to highlight the need for novel tools in studying newly emerged function spaces and boundary behavior of their elements. So I like this description very, very much. And then finally, two papers, actually, those are two papers but connected, closely connected papers, not yet appeared, but already online available. Let me mention this problem, which they consider here. This is the smallest enclosing ball problem in a general metric space. So if you are given a metric space and a non-empty closed bounded set B in the metric space, the problem is to find, if possible, the smallest closed ball in the space that includes our given set B. And the center of such a ball is called, if such a ball exists, the center of such a ball is called the Chebyshev center of B, and the radius is called the Chebyshev radius of B. And they consider here, and this belongs to matrix analysis, I mean, the content of this paper. So here they consider double stochastic matrices. The square matrix is double stochastic if every entry is non-negative, and if each row and column the sum is 1. Let omega n denote the set of all n times n double stochastic matrices. It is a convex polytope in the Euclidean space of dimension n squared, and it is shown, it's a famous result by Birkhoff, that the extreme points of that set are exactly the n times n permutation matrices, and for that reason, usually this omega n is called a Birkhoff polytope. The geometry of this set has been an active subject of research for more than half a century, and in those two papers they give important contribution to that line of research. In the first one, they consider the elements, so those are matrices, but they consider them as linear operators acting on Cn. And here, Cn is equipped, so Cn is equipped with the LP node, and on the matrices they consider the corresponding operator. And what they show is the following, that for all P's or all possible P's, the special doubly stochastic matrix, which is just the arithmetic mean of all permutation matrices, is the unique Chebyshev center of omega n, and they also compute the Chebyshev radius for p equal 1 and p equal infinity. This is 2 times 1 minus 1 over n, and for p equal 2, this is just 1. And in the second paper, on Cn, they consider the usual, the Euclidean norm, the L2 norm, but on the matrices they consider the so-called Schotten-P norm. I don't want to explain this. When P is infinity, the Schotten-P norm is just the operator. And they prove that, again, the special double stochastic matrix Jn is the unique Chebyshev center of this polytope, and the associated Chebyshev radius is equal to n minus 1 to 1 over p. So maybe I can show that Professor Mashregi's research activity is really very broad, and he contributed to our journal, published important papers also in our journals, and let me hope that this thing will continue. So thank you so much, and I congratulate you. Thank you very much.
Thank you very much. And now I would like to present the medal to Professor Mashregi. Please come forward. Mr. Light. And it is a tradition that the recipient signs a marble plaque commemorating the award. So I would like to ask Professor Mashregi to sign the marble. It's a marker. Signature. And I would like to ask Professor Mashregi
if you allow me to make some comments at this time. Thank you very much, Professor Olmar, for your nice introduction. Thanks to you, to the Institute, and all the members of the steering committee who chose me. I'm sure that there are many more of these very colleagues, and I'm very privileged and honored to have this distinction. And also, thanks for your nice introduction. I should listen to your talk again to understand my own work. As good as you did. It's recorded, so you can talk. And also, it's comment is not a gesture of being humble, but it's really a source of inspiration for ourselves in the future. I have another CV which I don't show to anybody, even lawyers doesn't have access to it. And if somebody wants to talk about that CV, it takes maybe 3-4 hours. And that's the CV of failures. And it's true, it's our life. Life is not just success, it's filled with success and of course rejection. I mean, emails that your group is not accepted, and several news which doesn't make you happy. But that's not the end of the world. And of course, I've received some reports that even made me cry. But a while after, maybe 2 days, 3 days after, I went back and read the report again and tried to improve myself. And that could be a source of inspiration, in particular for the younger generation. It's very normal, natural to receive unpleasant news, unpleasant emails, rejection for books, for papers, but our task is to learn from them and go forward and build a better future for ourselves. And the last comment, the slides that Professor Olmar showed, you saw them of collaborative. I owe them a lot. I didn't do all of this myself, and I thank them all in the French and English that I worked with them. And the results are large extent by them. Today, my goal is to talk about polynomial approximation in functional spaces without going into detail and just showing what's going on. And this is a branch of science that I've been with and collaborated with many professors and students and learned a lot from them. So, and this is the table of contents and classical results. Then I talk about 2 problems, density and schemes, but our focus is on scheme, a little bit of abstraction, and we can finish. Classical result. Why we consider polynomial? Let's just start with this question. It's a bit unusual to start with award ceremony with such a question. Polynomial is given and I ask you to evaluate the point 5. But that's the whole story. Bear with me, you will see that this is very important, even though it's simple. I changed polynomial to sign. You see, it's a different question. You are not able immediately to add, subtract, and obtain the result. You need something else, or with logarithm. It's different from polynomial. And there are functions that probably because of your domain, you never heard of it, like Jacobi function. And the senior member of the audience remember even in the high school, at the time there were some pages of tables of sine, cosine, and logarithm. That's approximation theory. We used to do approximation at the time. And engineers, any engineer had this tool on his desk. And they did a great job with it. Before we are flooded with all electronic devices like computers and stuff, they used this to build big houses. And they were very successful. And I mean, this is a very famous saying by John Neumann. Truth is much too complicated to allow anything but approximation. You have to approximate. And there are several tools for approximation. I just concentrate on analytic polynomials, but the branch is very wide and many different definition, or for example, the last one, Béla splines are, people in signal processing, they are working with that. So let's start with some results that we know, and probably we have been lectured in bachelor courses. The first one is, of course, the Weierstrass theorem, approximation of continuous function and polynomial. The theorem is so simple that we even teach it in first course in analysis. If you have a continuous function on a bounded interval, you can approximate it by analytic polynomial. And this result has been generalized, for example, by Stone, at least in two respects. First, not necessarily on the domain AB, an arbitrary compact Hausdorff space, and also replaced polynomials by another set of functions which is more general. Here is the result. The result is very simple to state, but it's very powerful too at the same time. X compact, a subalgebra which separates the point, very simple assumptions to verify. Then the conclusion is wonderful. A is dense with respect to the uniform space. And in particular, it works for the polynomial. That's for the real numbers. Now let's go to the complex plane. One of the earlier results is to Runge and approximate using meromorphic functions. And to explain Runge theorem, it's better to start with some figures. The goal is to approximate the function on a complex set, which is the blue, including the frontiers. And then we consider the red E, the set E, which is a discrete set. At least E has one element in each bounded component of the set. And the unbounded component is up to us. We can put or we cannot. But in each bounded we should have. And another important feature of this theorem is that we need an open set which is slightly bigger than the complex set. The complex set is inside the open set omega. Knowing all of this, here is the theorem. We have a function which is defined on omega, on the bigger set, and analytic inside. Then we can approximate it on K with rational functions. The importance of the set E is that the poles of E are coming from the dots that we chosen. In particular, I would like to emphasize on one feature of this, which is in red now. F is assumed to be analytic on something bigger. In particular, even if a set K doesn't have any hole, so our set E is empty, and still we want to approximate. When the set E is empty, the rational function is a polynomial. So we are able to approximate by a polynomial, but the assumption is that it's defined on a set bigger than that. And the theorem works. We can approximate a polynomial. And it was an open question for many decades. Can we remove this bigger set? Just assume that F is defined on K. And this was done not only very young, as I said, many years later, and the theorem said yes. If you have a set which doesn't have a hole, continuous on K, analytic inside, that's enough to be able to approximate by polynomial. There are many other results of this type, but I just mentioned a few to do the preparation. But now we move to the domain of functional spaces, in particular functional spaces which are defined on the open unit disk. And even though open unit disk sounds to be something small, but a lot of things goes there. And Abdan Saracen said, very celebrated mathematician, he has spent a much greater part of his life on the open unit disk. Many mathematicians do this. Here is the set. We have D, holomorphic function on D, and holomorph is big. The space is really large, but we consider something smaller. A Banach space inside this, and polynomials are in this Banach. Examples. For example, the first one is the Hardy space. But there are others like Dirichlet that we talked about, Bergman, Mulder, and the list is really long. Many other function spaces which are defined on the open unit disk. knowing this, there are two major approximation problems. The first is, of course, when the polynomials, are they dense over there? That's a rather straightforward, easy question to answer. Sometimes yes, sometimes no. We see both cases. But the second is more delicate. Assume that the answer is yes. And so the function f is given. We know that it can be approximated a polynomial. Give me those parameters. Something explicit. And we call this density and scheme or density or algorithm. So I want an algorithm whenever you know the answer is yes. So let's take some facts about density, but we concentrate more on the scheme. Density. Two techniques, duality and dilation, to verify if something is dense or not. For duality, we know we go to make Friedrich, who is the mastermind creating the duality theory for us. And I will mention at least two results. This is the first one, which is very standard technique. If you want to show that something is dense, you assume that the elements of dual are zero in this set, and then you try that they are zero everywhere. Consequence of that is that the set is dense. The standard, very, very powerful technique, and it works in all functional spaces that I mentioned. Also, as a prototype, I mentioned Saracen proof, the fact that polynomials are dense in Lagrange-Wozniak spaces, whatever that means. But the technique was this theorem of F which I mentioned. And also a rather recent result of Tom Ransford giving the lit proof of Sturm-Weierstrass. But there are many more examples. This duality technique is broad and applies to many sets. Dilation has a different nature. The function f is defined as a Taylor series expansion. When you replace z by rz, f index r, which is the dilation, is defined on this bigger than the original. And therefore, on the boundary t, which we might have bad behavior, now the function is analytic. And therefore, it has the best possible behavior. So we are able to approximate fr inside because it's analytical, and then use this to approximate f itself. So for several functional spaces, this works because fr is in x and fr approximates goes to f when r goes to 1. And here is the algorithm with dilation. First step, we approximate f by fr. Second step, we approximate fr by polynomial, and then we are done. But the good news is that this technique works in many functional spaces. Here is the list, and there are more functional spaces for which it works. Bad news is that it doesn't work all the time. And there are two reasons for that. The first reason, there are spaces which are not star-shaped. In other words, when we dilate, fr goes out of the space. This is easy to catch. But the second phenomenon is more difficult to catch. There are spaces which are star-shaped. In other words, when you dilate, you stay in the space. But quite surprisingly, when r goes to 1, f of r doesn't converge to f. And so the previous technique doesn't work. The first one, for example, modulus spaces, for example. For the second, which is more difficult to Lagrange-Wozniak spaces, provide an example. And this wasn't easy to catch. First time around 2010, the group of Szőkefalvi-Nagy and Ransford observed that there is a specific function f such that when the dilate lim sup is not finite. And it took at least 6 years for us, another group, to show that lim sup can be replaced by lim. It's not just replacing lim sup by lim. The technique is completely different, and we see now what's going on inside. And even they could remove the Blashney factor, which is inside, and work with output function. Now, the main topic of this lecture is the scheme. As I said, Here you assume the polynomials are dense, but give me the polynomial Pn. How can you approximate? And I need the formula for Pn. I present two methods, well, there are more. Taylor polynomials, and if they do not work, weighted polynomials. And again, we go back to Friedrich's technical duality that I mentioned earlier. So f is given by a power series, n goes from 0 to infinity. Why going to infinity? We stop at n. And when we stop at n, we have a polynomial. So we expect, and expect is in red. It shows that it's just expectation, it might not work. We expect that this polynomial converges to f when n. Not a bad expectation. For example, in Hardy space H2, the norm is defined by a convergent series of the coefficients, the sum of them. And when we do the difference of Sn of f, the polynomial minus f, the norm, just by the definition of the norm, is the tail of a convergent series. And when you have a series which converges, the tail goes to 0. It's somehow straightforward, you get it for free. And the same is free for the Dirichlet space. The d of f is defined a little bit differently. There is a factor k, and the norm is k plus 1. But still, when you do the difference, is the tail of a convergent series. Again, for free, it goes to 0, and it works even for the classical convergent space. But what about the other Hardy spaces when p is between 0 and infinity? And look at 0 and infinity. And h infinity just bounded unweighted function. Here is the answer. For p between 1 and infinity, not including 1, not including infinity, the answer is yes. Taylor polynomials are still a good candidate, but this is not absolutely not a trivial result. And to do this, we need to British brother, Marcel, who gave us an operator, a projection which is bound. And the proof is easy, just 2-3 lines, because the hard work is already done. The hard work is to show that this projection is bound. And here it's for you. We have a function LP, so it has a representation, but n goes from minus infinity to plus infinity. We chop half of the spectrum, either the positive part or the negative part, doesn't matter. For example, here the negative part is chopped, and we start from 0 to infinity. And Marshall Reeves theorem says that this operation is a bounded operation, and even I mentioned somewhere the norm can be controlled. Here is we have f hat, it's the spectrum of it, and then when we chop, half of the spectrum is 0, we replace by 0. And we know the formula up there, the norm of LP is controlled by the norm of P. That's the essence of his theorem. But why is this related to Sn, to Taylor polynomial? Here is the description which is easy to understand. Suppose that we have a function HP, already the negative part of the spectrum is 0, and we want to choose S2. S2 means the first 3 harmonics. We want to choose the red part and eliminate the blue part. Here's the way we do. First, we do shift to the left side by multiplying by n z to the minus 3, so the function shifts. And now we can apply this projection, either eliminate the negative part or the positive part. Here I want to eliminate the blue part, so I might multiply by identity minus the plus. So the blue part is gone, and now I shift it back. I shift it back, what remains is just S2. The magic of this is S2 is given by S2. And it can be generalized even for Sn. You have to bring this forward to continue. So why is this theorem very fundamental? Because we have 3 operators. 2 of them are multiplication by something unimodular, and the middle one is a Poisson-Louise operator. If you take the norm, and the norm becomes 1 normal 1 minus p, which is measured by 1 plus 1 of p, and the other is again 1. The norm is controlled. The right side doesn't depend on n, and this is important. And the reason it's important is because of this algorithm scheme. If you have Tn, a sequence of Boolean operators, for ours is Sn, such that Tn, its image is a polynomial. But the second is important. The norm of Tn is uniformly bounded. And for every polynomial Tn of p goes to p, then for every function Tn of f goes to f. In other words, we have the scheme that we are looking for. And the proof is very easy. The proof is in epsilon over 3 triple analysis. We want to show that f minus Tn of f is small. We add and subtract some terms, take the norm, and the magic is that in the last part we replace Tn of p minus f by something which doesn't depend on n. And now we can choose p such that the first step and the last step are small. And as soon as we choose this, we choose n big enough such that the middle term is small, we are done. So straightforward, just because that norm didn't depend on n. In our case, thanks to this theorem, Sn is bounded by constant, and Sn of p is something more than convergent to p, is equal to p, because when the degree is big enough, we have all the coefficients. So it's become equal to p, and therefore for every f, it works and we are done. Wonderful. What about the other two cases, h1 and h infinity? Band effects. It doesn't work for h infinity. I can give you two proofs in one slide. The first proof is that h infinity is too big. If a space is, the polynomials are dense, it has to be separate. And h infinity is not. So polynomials are not dense. The second, again, a theorem in analysis 1. If you approximate something by continuous function uniformly, that thing is also continuous. So in h infinity, we have many functions which are not, like infinite Nash-Lemma, singular function. They are not continuous on the boundary, so they cannot be approximated by polynomial. So as a mathematician, we change the question. Instead of considering, h infinity, there are two ways. Either we sacrifice the topology, or we sacrifice the space. Here, I sacrifice the space. Instead of h infinity, I go to something small. The closure of the polynomial. Then, by definition, polynomials are dense. But the natural question is that yes, we know that by definition polynomials are dense, but do Sn fulfill a good candidate for us? And the answer is no. And this is again a good result. To do this, now we look at Sn not as a polynomial, we look at it as an operator. Operator working on this algebra, image on the disk algebra, and the norm of this has a name, it's called Lebesgue constant. What is Ln? What is the Lebesgue constant? Here we can work with kernels and some techniques from elementary operating theory to show that Ln is given by this formula. Not that much useful, you don't see how it goes. There are other formulas, for example, by Hardy, two integral formulas, useful for other facts, but not useful for our purpose here. Another two summation formulas by Anthony Ziegler. Again, we don't see what's going on. But there is one formula by Watson, which is useful for us. Ln, the formula says that Ln grows like lagrange. We see it here. The difference between Ln and this combination of log is a constant. Or put it this way, Ln is bounded below or above by some constant log n. And so when n grows, the norm explodes. The norm is not finite. And what can we say when the node or the sequence of an operator is not bounded? Here we need a theorem from Banach and Steinhaus. Of course, global boundedness implies global boundedness, but the other way around is essential. If you have local boundedness, you have global boundedness, and we teach it in functional analysis. Usually the other way around. Usually we teach that if we have a sequence of operators which are locally bounded, then we are globally bounded, which is equivalent to this one. If you have a sequence of operators which are not bounded globally, then at least at one point they are not locally bounded. And here is what we need. They were not globally bounded. So there is one point such that Sn over f in norm is not bounded, therefore it doesn't converge. And the history of this goes back even to Bohemond. The goal was something different. He wanted to show that at the time, in 1870s, was early days of harmonic analysis, they thought that Fourier series behaved well for a nice function. A nice here means continuous. If you have a continuous function, it's nice, so the Fourier series should converge. His goal was to construct a continuous function such that the Fourier series diverges at one point, and he succeeded. This is his construction. But it's very easy to modify this construction and find what we are looking for and answer our question. Now, if the Taylor conclusion, the Taylor series not work. So what is the remedy? The remedy is another scheme, which is Chazar scheme. This is a lecture from calculus. We show that this series is divergent by calculating Sn. Sn is oscillating, so it doesn't converge. But Chazar did this technique, averages of the partial sums, not the partial sums. When he took the averages, it was convergent. And therefore, sigma of n goes to half, and if you calculate the averages, you see that it's equal to the sum of an, but we add the blue term, something which is an innocent-looking coefficient, but by adding them, the history completely changes, and this is a convergent series. And the notation is that we say that sigma an is convergent, but C convergent, Chazar convergent to this. In our case, the sum of minus 1 to the power k is a half, but in Chazar, what about summation of the entire series? Again, we need somebody from here. He applied it to entire functions and created something which we call it Taylor polynomials now. You see again that blue term. Instead of considering Taylor polynomials, it seems innocent, it seems it doesn't have us, but it changes completely the feature. And by doing this, I recall you that we saw that in the case of H1 and in the case of this algebra, Taylor polynomials are not good, they do not converge, but Hardy showed that if you add those terms, if you use Taylor polynomials, it's a convergent scheme. And even more than that, we can generalize this concept and introduce what is called sigma and alpha. It depends on the parameter alpha. And alpha is such that if you put alpha equal to 0, you obtain Sn, Taylor. And if you put alpha equal to 1, you obtain sigma and Chazar. But it can be anything even real. Usually we take it for alpha bigger than -1. And the generalized version of Hardy-Gilbert theorem is that these generalized Fourier Taylor polynomials also are good candidates and they converge to function. And this goes back to rather essentially ago. And just to show you that some recent results, my result with Tom for Dirichlet spaces, but harmonically weighted Dirichlet spaces. We showed that failure polynomials are the right candidate. Taylor polynomials do not work. It was an open question. And quite recently we showed this. If you go to this book of Hardy's last book, there are many, many more schemes that can be applied. To finish this part, duality again, we need this technique. What is the duality? We have the space X and the dual. Sometimes the space gives something to the dual, and sometimes dual gives something back to the space. And you see they discuss each other. I give this to you. I said, no, I give that one to you. Interestingly, we found something that both gives to each other. In our language that we discussed today, if we have an algorithm in X, under some condition, this algorithm can be transferred to the dual, or vice versa. If there is an algorithm in the dual, we can transfer it back to the space. Here is, I talk about series in X and X star, and SNA, SNA star are just two schemes. Don't forget about the formula, just two summation methods. And also the theorem, which is, very fresh baby. Don't look at the details. The important thing is the blue part. The following are equivalent. And look what are equivalent. Sometimes you see X, sometimes you see X star. So the convergent in X is equivalent to convergent in the dual with different topologies. That is why I have this. For this concept, no one can say that I gave to you. Both give to each other. Read this theorem without going into detail in this way. If you have a convergent scheme in one of the spaces, then the convergent scheme can be transferred to the other space. And let's apply this to this table. Some X dual and even the second dual, continuous function, for example, the measures, or the dual of disk algebra, there are two realization, either as quotient space or as a quotient space. The third one I would like to explain a little bit more. VMOA is dual Hardy space H1, and the second dual is BMOA. And the last one is for the Bloch space and Berger space, little Bloch and big Bloch. But let's apply the theorem that we saw, the theorem for this line, VMOA, H1, and BMOA. And you remember it was X star, but it can be even X double star, because if it goes from both ways. And the result is like this. Again, we don't need to go into detail. The important message is the following are equivalent. And what are they equivalent? If you have a scheme or algorithm in one of these spaces, then the algorithm can be transferred to the other spaces. If something works, the technique works in H1, you can transfer this technique to BMOA, you can transfer it to VMOA under Wittgenstein topology, under big topology, or even under the norm topology, which is quite surprising that you can go back and forth within all of these spaces. A very concrete application of this we saw in a previous slide that in H1, Sn doesn't work, but sigma n Feger polynomial works. So apply this in the previous theorem. The following are equivalent. The first one, we know something it works in H1. So we apply it in the other, and here is the result. It comes for free. That the Feger polynomial works for VMOA under the norm, and works for BMOA under the Wittgenstein topology. So that's the good thing about this. Again, everything boils down because we have the duality technique. is worth times 2 this. Is my time over?
No, I don't think so.
Okay, I can continue 5 more minutes.
Yeah, sure.
That's the last one, abstraction. We saw some functional spaces, which of them represented approximation of scheme, and it was simply a family of operators from X to X. The image is a polynomial, and that polynomial converges to an example we saw. For example, in HP, or in the Dirichlet space, we saw Sn. And in the case of this algebra, we saw failure polynomial. These are the scheme. And here is a table which describes more that obtained an interesting point, the red one. We will see in the Ramshoff spaces, there is a theorem which we'll talk about it. We know that the scheme exists. It's an existence theorem, but we don't know what it is. It's more than 20 years that we work on it, and still we don't know. It's an open question. Another interesting question which I'm able to answer and finish my lecture, in all cases, even if we fail, we continue a little bit and we obtain another scheme. For example, if Taylor didn't work, we obtain failure polynomials or others. Is there a space X which absolutely doesn't have a scheme? No scheme works. And thus, each functional space is equivalent question admits a scheme. And to answer this, we need a concept from Banach space theory. This result says that it's equivalent to a property which is called bounded approximation property. I explained what it is. But the proposition is rather simple. It says that you have an algorithm, you have a scheme, if you have a bounded approximation property. Of course, the first condition is natural. The polynomial must be dense. But the important thing is BAP property. What is the BAP property? In a Banach space, Tx minus x in norm is less than epsilon. Look at this in this way. X is the same as identity. So we approximate the identity operator for not for x, all x, for x in K. So we approximate identity on compact sets. By what? By operator T, which is finite rank. So if you are able to approximate identity on compact sets by finite rank operators, we say that it has a finite approximation, the approximation property. Of course, the norm of T here depends on K, depends on epsilon. If there is a space for which we can do this approximation, and moreover, the norm is uniformly bounded. There is an M which controls for every K, for every. That's the word of bounded. We call it bounded. And for example, if a Banach space has a shorter basis, then it has bounded approximation property. Or, I mean, in particular in Hilbert space, because it has an autonomous basis. Has this property. And as a corollary, if you have a Hilbert space, so you have an autonomous basis, so you have bounded approximation property, and by that proposition there is a scheme. So any Hilbert space of function automatically has a scheme. The branch Ovniak space is a Hilbert space, so by that corollary, it has a scheme. We don't know. I mean, it's 20 years that we work on it and we fail. It's a very large open question. And back to the big no red. If you want to find a space which doesn't have the approximation property, so you need a space in which the polynomials are dense. It doesn't have a scheme. You need a space which polynomials are dense, but doesn't have the bounded approximation property. And this, in another context, was answered by Elfilo in the 70s. It was a very important achievement at the time. He presented separable Banach spaces without bounded approximation property. And later on, by Reed and other examples in little p or in C0. The construction is abstract, but I need a functional space, not an abstract. And that is why we have this. It's, I like this theorem. With Tom, we did it for Banach spaces. Joseph Domet, he did it for Fréchet spaces here after generalized over result. But the result is interesting. Remember at the beginning of talk, when I talk about holomorphic function on D, I said that the whole D is gigantic. It's a very big space. And there are several ways to justify this. One of them is this. And this theorem has a very interesting message. It says, pick any centrable Banach space you wish. Doesn't matter. Any Banach space. Central. Then there is a copy, and not just a copy. Isometric, isomorphic. Both. There is an isometric isomorphic copy inside whole D. And that is why I joke with my friend who work in Banach space theory. I said, forget about it, just study complex analysis, it's enough. Because all Banach spaces are there. And it really shows that whole D is really, really big. All Banach spaces are there. And even there is an extended version of this. Even we can control the norm of the monomials. I mean, even more than that. And knowing this, we can answer that no question. Because Elfilo did the big job. He created a Banach space which doesn't have the bounded approximation property. By this theorem, we have a copy in OD, which is a functional space, polynomials are there, and doesn't have the bounded approximation property. And therefore, no algorithm work. So it's very strange phenomenon. You have a space, polynomials are there, dense over there, but no scheme of the type that we saw works over there. And here is almost the end of my talk. It's not a mistake, it's not a typo. Odd functions. The odd functions which are odd. It's a continuation of that work. It's a Hilbert space of functions. So, and this Hilbert space, odd polynomials are there. But there is an odd function which cannot be approximated by odd polynomials. So what does it mean? Look at this summation. Sn of f is the partial sums of f. So partial sums of f is an odd polynomial. Choose alpha and k the way you wish. For example, if we choose 1 minus k over n plus 1, is the failure polynomial. There are many other options. Doesn't matter. Completely free. Whatever we want to choose. But at the end of the day, Tn of f will be an odd polynomial. Whatever is your choice, for sure Tn of f will not converge to f. So it's an odd function which cannot be approximated by any combination of its partial sums. That is why it's entitled odd function. Thank you very much.
Thank you very much for the talk. Are there any questions, comments? While we are waiting for questions, I do them.
Together is great.
So maybe not through the question, usually I would see the questions and this would be one of the So that's called multivariable, the case of multivariable functions.
For nicer spaces, like I started in H2, when the norm is defined by coefficients, then it works in coefficients. I mean, you can, for example, if you are in y-disk or dm, then you have expansion.
Oh, yeah.
Norm. And one of the ways to generalize the hard disk based on H2 of dm is to write this. And in that case, everything works well, the table. A bit of generalization of failure also works. But if you go even further, in the most general sense, maybe of this question in multivariable and still have an investigation.
You mentioned that there was an open question concerning Hilbert space. What happens if these leads or inner functions are in the classical?
For this it works, because then B is an inner function, HB becomes what we call modern space, and it's a closed subspace of Hardy space, and it inherits the topology of H2, and everything works perfectly well. But in other cases, the topology is completely different. The topology is stronger, and in that case, it doesn't. And I said linear approximation because we have a scheme, we have an algorithm which works. In other words, function f is given, you are able to construct polynomial p, but it's not linear. If you change your f, the technique changes, it's not a linear formula like fail. So a non-linear scheme exists. A linear, and explicit formula. A linear one in theory we know it exists, but we don't know the formula.
This last space about the art, it's a construction, right?
Yes.
Not a natural.
It's not, it's pathological. It's kind of pathological construction, but knowing that it exists,
It's very strange.
it's very strange. We ourselves, we couldn't believe that, but that's the way. Because, I mean, naturally in our head it's like this. You have a space, you know that the polynomials are dense. So there is a sequence of polynomials which converges to your. And so if your function is odd, that sequence should be a sequence of odd polynomials, not with partial size.
Further questions? When you've got that, thank you very much. And I would like to thank everybody for participating. Thank you very much for coming. And I close the ceremony and see you.